Hey guys, today we're going to be talking in depth about work, which I know is a topic we've discussed on several occasions, but we're going to be looking at it a little bit more closely here today on our work notes. So, first off, there are two types of energy transfer between objects. The main one that we've been looking at is work, but there's also another one, and that is heat. Now, heat transfers thermal energy specifically. So that happens based on a temperature difference between objects. The work transfer is a different kind, and that is specifically mechanical energy. Now, if you remember from our lesson a few times ago over energy types, mechanical is not one specific type. It is instead a whole category. And as a category, it includes both kinetic and or potential energy. So both of those are under the umbrella of mechanical, which means when you do work, you can either give something kinetic energy or potential or both as a combination. So the way that we actually do work as people or as machines, because machines can also do work, how we do work is we have to push objects. For example, if we wanted to do some work on an object to give it more kinetic energy and speed it up, we'd have to push it to speed it up. Or if we wanted to give an object more potential energy by raising it up, we would have to do work to raise it up. We'd have to use a force to do that. Now, when that happens, it also happens over a specific distance, which is kind of a weird thing to bring into this, but it happens over a distance. So whenever you do that, the object's energy changes. And it can be written very, very simply. And that is with this equation. It is a W for work. Thank goodness for normal variables. That is work. It is measured in joules still. And it is equal to the force that is used times the distance that the object is pushed over. And force is measured in newtons, and distance is measured in meters. All right, so there is a note here, and it says that the force and the distance must be blank. And the answer for that is non-zero. Okay, force and distance must be non-zero. The reason for that is mathematical. If you plug in a 0 for force and multiply it by any distance, if you use no force over 100 meters, you've done no work because it's 0 times 100. Or if you push really hard, you push with 100 newtons of force and you get nowhere, a distance of 0, you're doing 100 times 0, which is still 0. So the force here and the distance both have to not be 0. If they are 0, either one, no work is done. No work is done. Okay, so the other options besides no work being done is that work can be positive or negative. We've looked at this a whole lot over the past few days, but there are some extra conditions here today. So for positive work, the force and the distance are in the same direction. And usually when I'm in the classroom, I show some physical demonstrations of this, but I'm not there, so I can't do that. But imagine, if you will, an object that's moving to the right. Okay, if you want that object to speed up, you have to push it to the right. So if you want to do positive work and give it extra energy, you need to push it to the right, which is in the same direction that it's going. And what that's going to do is add energy to the system. So the grammar here is energy is added to that system. Now, negative work is trying to take away energy. So for that, the force and the distance are in opposite directions. So if you wanted to take energy away from something, you have to push against it. So here that is energy is lost by the system in negative work. The force and the distance are in opposite directions and energy is lost by the system. Now we've got some semi-interesting examples to think about those things. This first one says you are holding a 20 kilogram box at chest height. How much work are you doing? And this one's kind of a trick. Some of you may already know the answer, but you're just holding it at 20 kilogram or the 20 kilogram box at chest height. You're holding it there. How much work are you doing? Well, the questions for if you're doing work involve, are you using a force? Do you have to use a force to hold a 20 kilogram box up? Yes, in fact, you do. But when we think about the distance component of it, there is no movement. So it does not change height at all. If it doesn't change height, it doesn't change energy. And if it's not changing energy, you're not really doing any work. So the answer here is 0. And you can get that from two different directions. You're using a force, but you're not moving a distance. So any force multiplied by 0 is 0 work. But also from the standpoint of energy. You're holding it at the chest height. It's not speeding up. It's not slowing down. It's not moving up. It's not moving down. So it's not gaining or losing potential energy or gaining or losing kinetic energy. Kinetic and potential both stay the same. So no work is done in that case. Now on these other ones, we will have some work done. So we do have the guess method boxes to see what's going to happen there. So example number 2 here, part A, says you push a 20 kilogram box from rest with a force of 4 newtons across a frictionless surface over a distance of 3 meters. The question is, how much work did you do? So the object here, or the system, is the box. And what are the things we know about it? We know that it has a mass of 20 kilograms. We also know that it was moved from rest, so that's an initial velocity of 0. And we know it was moved with a force of 4 newtons. And we know that it was moved with a distance of 3 meters. The question is, how much work did you do? Okay, so we look at that and we say work equals force times distance. That's our equation for today. That's pretty easy. All right, we got work equals, the force is 4 and the distance is 3. 4 times 3 is 12. Easy peasy on that one. That's just multiplying 2 numbers together. But the more interesting thing comes from this question B. What is the final speed of the box? Final speed of the box. Object is still the box. We've still got a mass of 20, an initial velocity of 0, a force of 4, and a distance of 3. But we've kind of already used those pieces of information. And now we also know the work was 12. Now note here that it was a positive 12 because we were pushing it from rest and it was going to be gaining energy in that case. So what we need to do here is go back to our old work kinetic energy theorem, which is 1/2 mvi squared plus w equals 1/2 mvf squared. Because we're dealing with kinetic energy, this box is moving from rest and speeding up, and we're doing work on it, and we're looking for a final speed. So we're moving back to that old kinetic energy work theorem from a few days ago. When we plug in, we're going to get 1/2 times 20 times the initial velocity squared, and that initial velocity was 0, so really that's going to cancel that whole term out. Plus 12 is how much work we were putting into this. And then that equals 1/2 times the mass of 20 times the final velocity of unknown, which is squared. Then we have to do our math. So really on this left side, all we have is 12. Over here, 1/2 times 20 is 10. We've got our VF squared. So we're going to divide by 10 first. And that's going to give you 1.2 equals VF squared. And then we have to take the square root. And then I'm going to need to stall for a second while I go get out my calculator. I know you guys are usually the ones that do the calculating for me, and I very rarely have to type it. But today, since I'm alone at my house and y'all are there by yourselves, I have to do my own calculator work. And the answer that we get here is a final velocity of 1.095, which will really round to 1.1 meters per second. Okay, so that would be the final speed of the box here. Note that we had to find the work first, and then we also had to use that work in our old work kinetic energy theorem that we'd already worked with. All right, things are about to get a little bit dicey in some of our next few scenarios. Okay, question 3 here says you push a 20 kilogram box from the ground to a height of 3 meters on a ramp that is 12 meters long. The question is, how much work is done on the box? So our object here is once again our trusty old box. But we've got some kind of weird information this time. We've got a 20 kilogram box. That's the mass. That's pretty normal. And it's pushed from the ground. So from the ground is going to tell us our initial height. And on the ground, your height is 0. So height initial is 0. to a height of 3 meters. So height final is 3 meters on a ramp that is 12 meters long. So that new piece of information is going to fit in with our work stuff today as distance. The distance you push the box over is 12 meters. So some of you might need a picture at this point. This is what's happening. We've got a ramp here. The ramp has a height of 3 meters. So it gets you from the ground up to 3 meters. But to do that on a ramp, your whole ramp length is actually 12 meters long. Okay, so things there are a little bit strange. But the distance you push the box over is 12 meters and only gets it up to a height of 3 meters because you're on a ramp. And the question is, how much work is done on the box? Now, there are really two ways that we can find work. We could approach this from two directions. The one that we're mostly looking at today is the one where we say work equals force times distance, but don't write that down because it's not the right one for this time. Okay, so that's the one for today. But that doesn't work because we don't have the force. We only have the distance. So we're going to have to go back to an old method that we used last class period, and that is working with potential energy. So we also had work in our work energy theorem equations. The one from last class was the potential energy theorem. So that was MGHI plus work equals MGHF. That one's relevant here because we have a box that's changing its height, or someone's changing its height. So we have a change in potential energy and work is being done. And we can solve for work this way instead of the way that we learned today. And we'll use that way we learned today down below in a second in conjunction with this. So the work done on the box can be approached from this energy standpoint. We can see how much energy was added to it and call that the work. Now we've got the mass, that's 20, gravity is 9.8, and the initial height is 0. So really, all that's going to cancel out because it didn't have any potential energy to begin with. Plus, something did work to it, moved it up this ramp, gave it potential energy there at the top. And then we can find the potential energy using this MGHF on the other side. That mass was 20. Gravity was 9.8, and the height final was 3. So I'm going to pull out my calculator for that one. Really, all we're doing is multiplying these numbers together. 20 times 9.8 times 3 is 588 joules. So the person, in pushing this box up the ramp, has done 588 joules of work. Now, part B is going to use that information with the stuff that we learned today. Now, I know the question's gone now, but we've got all the relevant information. It says, what force was used to lift the box? So for force, the only equation that we currently have involving that is the one we learned today, that work is equal to force times distance. So we're going to need all those values. Our work that we just found was 588 joules. And our distance from the ramp, we have to go back and look up at it. The distance from the ramp was that the ramp is 12 meters long. So we're going to scoot that up and say distance is 12 meters. Question is, what is the force? And then easy peasy, we plug some stuff in there. Work is 588 joules. The force we don't know. The distance is 12. All we got to do is a little division for that. 588 divided by 12 is 49 newtons for the force required to push that box up the ramp. All right, so to recap what we did here. On that first one, we couldn't find work using force and distance because we didn't have the force. So we found it using the work potential energy theorem, which says we started with some potential energy, did some work to it, and got some other potential energy out. And that's what we covered last class. So we kind of had to go back to that old knowledge. And then for this second example, we took our answer from part 1 or part A, where we found the work and then used that with our new equation today, work equals force times distance, to solve for that force. Now let's see that all again one more time on number 4. And we're going to try to be a little more advanced on this particular one. Number 4 says a 5 kilogram object is moving with a speed of 3 meters per second. How much force will you have to use to make it stop within a distance of 5 meters? Okay, so let's look at all our information here. We have a mass of 5 kilograms. And it is currently moving with a speed of 3 meters per second, but we're going to try to get it to stop. So we have a VI and a VF. The VI is the 3 meters per second that it's moving at now. The VF is the 0 meters per second that we're going to use to make it stop. And it says within a distance of 5 meters. So we're trying to make it stop over the course of 5 meters. The question is looking at how much force we're going to have to use for that. So this one is kind of wacky. We're doing it on the day about work, and it doesn't mention work at all. But what we're going to have to do is combine our work energy theorem from the other day with the work we learned today to solve this particular question. Now, you could do this in 2 steps, okay? So if you were going to do this in 2 steps, the first step you would do would be find the work, and that would be using our long equation, 1/2 mvi squared plus work equals 1/2 mvf squared. That will let you find the work. And then you could find the force by saying work equals force times distance, just like we did up there on example number 3. That was like part A and part B. But because I know some of you guys can handle it, we're going to do this all in one step in a way that's a little bit more advanced and kind of bypasses that intermediate value of the work. So let's start off with our basic equation. We're dealing with kinetic energy here because we're dealing with speeds. Okay, so let's look at that. Our kinetic energy theorem says 1/2 mvi squared plus work equals 1/2 mvf squared. And if you remember conceptually, what this says is we start off with some kinetic energy, do some work to change it. And in this case, remember, we're taking away that energy. So the work is really negative. And that equals a new kinetic energy over here. But what we can do today is make a swap. We're going to take that work, and instead of writing it as W, we can write it as force times distance, because that's what we learned today, is that work is the same thing as force times distance. So we can just plug that directly in here to our 1/2 mvi squared. And now it's going to read 1/2 mvi squared plus F times D, not plus W. And that equals 1/2 mvf squared. Okay, so we just did a swap. We took W out and we put FD in its place. And that's going to let us solve this all in one go instead of finding an answer in the middle. And then we plug everything in. We've got 1/2 mvi squared. M is 5. Vi is 3. That's getting squared. Plus, we don't know the force. We've got a distance of 5. That equals 1/2 times 5 for the mass times 0 squared, which is going to cancel all that term out because it's not moving at the end, which means it has no kinetic energy. And then we just got to do a little bit of math from there. First off, we have to do all this multiplication. 1/2 times 5 times 3 squared. If you do the math, that turns out as 22.5. That is plus 5f, or f times 5. I'm going to rewrite that as 5f. But you can leave it as f times 5 if you like. That equals 0. Now from here, we're going to have to subtract 22.5 because it's added to our 5f. And now we've got 5f equals negative 22.5. That point, we're going to divide by 5, which is going to give us a force of negative 4.5 newtons. So really, when we did this one, all we had to do was say, we're looking at kinetic energy. Kinetic energy is the thing that's changing around here. And since we're changing kinetic energy, we are going to use the work kinetic energy theorem, which is this equation up here. We substituted in force times distance for the work, and then we solved it out for a force of negative 4.5 newtons. Now, you might be wondering, why did we get a negative force? And so if you think about it, the reason we got a negative force is that we are trying to slow this object down. So we're going to push against it. That's what a negative force means, is that we're pushing against it. And that also would give us a negative work, which makes sense because we're trying to take energy away from this object. So we get a negative force on that one. Okay, guys, I know that was probably a lot, and it is kind of hard to navigate your way through these equations. You now have three different equations to use. You've got the work energy theorem for both potential and kinetic, and then you've also got this new work formula for today. So you're going to have to really think through what your givens are and what you're looking for and which equations kind of match that situation that you've got. And I know that's a lot. So for your practice, it's just like a regular practice. You're going to do all the questions and then input it into the quiz to make sure that you're getting those right. And you can continue to resubmit that quiz until you get all of the answers correct, or as many as you can to get the score that you're looking for. All right, guys, I'll see you next week. Hope you're staying safe. Hope you're staying warm. And I hope you have a good weekend. Bye, guys.